Hey guys, on to part 4 of the chapter 9 slides, and I'm going to try to go a little bit faster through this because the last video got way too long, so let's get started with this. So, to refresh, when you're doing conservation of energy problems, there are 3 questions you need to ask yourself to determine what types of initial and final energies you have. So you look at your initial sketch, and you look at your final sketch, and for each one you ask these 3 questions. So what's the question you ask for kinetic energy? The question you ask is it moving? Because if it's moving, that means it has velocity and it will have mass, so it will have kinetic energy. So what's your question for GPE? The question for GPE is it at a height greater than 0? Because if h is greater than 0, then that means there will be GPE. If h is 0, this whole right side is 0, therefore the left side is 0, so there's no GPE. And finally, if you're dealing with a spring, what's the question you have to ask to determine if there's EPE or not? The question is there a spring that is extended or compressed? Because if X does not equal 0, then EPE won't equal 0. So what is Newton's second law of motion? This is the most important thing you will learn in physics all year. This is, of course, F equals ma. This is chapter 9. Last chapter was chapter 8, where we did momentum. What is the law of conservation of momentum? It looks just like this. Sigma p initial plus sigma j external equals sigma p final. So sum of your initial momentum plus sum of your external impulse, remember j stands for impulse for some reason, equals the sum of your final momentum. And then this chapter, the big idea is, what is the law of conservation of energy? Well, it looks a lot like the law of conservation of momentum, only we've replaced the p's with e's and we've replaced the j with w. So sum of initial energy plus sum of external work equals sum of final energy. So physics is making you one with everything. These are the big ideas we've learned so far this year. These are the things that apply all the time, everywhere throughout the universe. Newton's second law, the law of conservation of momentum, the law of conservation of energy. There are others. There's a law of conservation of angular momentum. There's a law of conservation of charge, conservation of isospin. There's a bunch of quantum mechanical things. Those are the big ideas. These are the ones we've learned so far in Physics 1. So the problem we're going to deal with is we've got 3 frustrated physics students, Alice, Billy, and Charlie. They're each standing on top of the roof, and they're 25 meters above the ground. They're going to throw their TI-84 calculators off of the roof at 23.2 meters per second. So Alice is going to throw hers straight up in the air. It's going to go up, come down, miss the edge of the roof. Billy's going to throw his out perfectly horizontally, so out like that. And Charlie's going to throw his straight down to the street. So we're going to use the law of conservation of energy to determine the final velocity of all 3 calculators. And as usual, we're going to ignore air resistance. So how are we going to do that? As usual, the first thing we've got to do, let me find my pointer, is step, What are we solving for? We're solving for the final velocities of all 3 calculators. So I'm going to write V final equals question mark, and the units for V are meters per second. So now we do step 1. All year long, step 1 is make a sketch. So here's the edge of the building. Still having trouble drawing straight lines. Not very good at the Wacom tablet. Let me try this again. Okay, that'll have to do. So there's Alice. She's going to throw her calculator. She is going to throw hers straight up. So we're going to give speed lines below. It's going to go up in the air, and eventually it'll come down. So this, I should write the word initial here. For some reason, writing is easier than drawing straight lines. All right, so there's our initial sketch. I'm going to leave out all the details to try to save a little bit of time. Our final sketch, what's going on in the final sketch? So final sketch, here's the edge of the building. Here's Alice. Her calculator, we stop the problem right before her calculator hits the ground. So here's her calculator. Here are the speed lines. Now we go on to step 2. Step 2 in an energy problem. Why did that not be blue? Okay. There we go. Step 2 in an energy problem is write the law of conservation of energy. So sigma E initial plus sigma work external equals sigma E final. So what you do is you look back at your sketches and you ask yourself 3 questions. So initial sketch. First thing, is it moving? Yeah, there's speed lines. If it's moving, that means we're going to have kinetic energy. Second question, is it at a height greater than 0? It is. I didn't write the heights in on these sketches, but it is at a height greater than 0. That means in the initial sketch, we're going to have GPE. And the final question is there a spring that is extended or compressed? There's no spring at all, so there's no EPE. So that's that. Now we go on to work external. Well, it says in the problem right here, we're ignoring air resistance. So that's going to be 0. So there is no work external. So we're done with the left side. Now the right side, sigma E final. So look at your final sketch and ask yourself 3 questions. First question, is it moving? Yep, there are still speed lines. So that means KE final is going to be something. Second question, is that at a height greater than 0? No, it's at its lowest height, so we would call this height 0. We would call this height over here 25 meters. But yeah, in the final, it's at a height of 0, so we don't have to worry about GPE. And there's still no spring, so we don't have to worry about EPE. So we're done with that. Now, let me pick a green. A nice green. That looks like a nice green. Step 3. Step 3 is the math. Okay. So turn the things into the things. KE initial is going to become, if you remember your formula for kinetic energy, 1/2 m V initial squared plus GPE is going to be mgh initial. And on the right side, KE final is going to be 1/2 mv final squared. So the thing we're looking for, if you go back to step we're looking for final velocity. So we're trying to get this guy right here by himself. So we've got to do the algebra. So first thing is let's divide everything by m. If you do that, something wonderful happens. The m's all go away. So I'll rewrite this without the m's. So 1/2 m divided by m is nothing. Well, it's 1. So that goes away. Plus mgh divided by m is just going to be gh. And the right side, 1/2 v final squared. So we've got more algebra to do. Next thing is we're going to multiply both sides by 2 to kill off this 1/2. And do this carefully because people like to forget something here. So if I multiply this first term by 2, well, the half goes away. And I just have v initial squared plus, this is what people forget. If you're multiplying both sides by 2, you've got to multiply everything by 2. So you need to have a 2 here. That's going to give us 2gh initial. And this is all equal to, well, we multiply this side by 2, so the half goes away. So we have v final squared. So next thing to do, take the square root of both sides. And once you do that, you're going to end up with, I'm switching left to right, v final is equal to, ignore the plus or minus, the square root of v initial squared plus 2gh initial. So now we've got to go to the numbers, is equal to the square root of, v initial was 23.2 meters per second. So 23.2 meters per second. That gets squared. Plus 2 times g, which is 9.8 meters per second squared times h initial, which is 25 meters. So if you do all that in your calculator, let me pick up my calculator real quick. 23.2 x squared plus 2 times 9.8 times 25. That gives you 1028.24, but you've got to take the square root of that. So raise that to the 1/2 power, and you end up with, okay, it's getting laggy. I already wrote a V. There's my V. V final is equal to, come on, it won't do. I'm writing and it's lagging behind and it's driving me nuts. Every time I touch the pen down, it's getting laggy. All right, that'll have to be for our equal sign. Anyhow, if you do this, you end up with 32.1 meters per second. Put a box around it. We solve for the right thing. I'm comparing this to we solved for the right thing. We gave it the right units. 32.1 meters per second. Do the bloody cheetah. That's about 64 miles per hour, which is fast. But remember, she threw it at 23.2 meters per second, which was 46 miles per hour. So it makes sense that it's going faster. So that is actually a reasonable number for this. So give it a check. We're happy about that. Now, we've only done one of them. So I'll just talk quickly through this. If we were to do this for Billy, we would have a similar drawing, only Billy's calculator. I don't know what the hell, I got the pen, I'll draw it. Billy's calculator, his would go straight out sideways like this. And at the end, his wouldn't land right where Alice is because it would do something like a parabola. His would land out here. Sorry, that's part of the drawing. So his would land out here, and we'd go back to step 2. We'd start with the conservation of energy. We'd write the same equation. We'd get the same algebra. We would do all the same algebra. And for Billy, we would also get 32.1 meters per second. Then for Charlie, he would throw his straight down. Let's pick up nice dark purple magenta. That's cool. He would throw his straight down. So his would look like this. And then his would land exactly where Alice's did land. So that would be his sketches. We would get the same conservation of energy. We'd get this line would be the same. We'd get the same algebra. We'd do all the same stuff. And we would end up with the same number. So kind of surprisingly, all three of them would end up at 32.1 meters per second. So click through all this stuff. Yep, 32.1 meters per second. So if you were to actually do this in real life, you would find that they wouldn't all have the same final velocity. Intuitively, this feels a little weird that one throws it straight up, one throws it straight sideways, one throws it straight down, and yet they all hit the ground with the same velocity. That's not actually very realistic. So why isn't it realistic? It's because we've ignored air resistance. So the question is, if we were to consider air resistance, where would that term show up in the law of conservation of energy? No, I put my mouse there already. Yeah, it would show up right here. That would be external work. So you'd have this. This wouldn't be 0 this time. Instead, we'd have to deal with this term. And you would get this down here. So this would be a negative term. So what that means is you would have less total energy on the left side, which means you therefore will have less total energy on the right side. Your kinetic energy final would be smaller, which means your calculator wouldn't be going as fast. So if you actually did this, Alice's would end up being the slowest, Billy's would be second slowest, and Charlie's would be fastest. So the very weird thing is the math for calculating air resistance is really hard. It's basically impossible because the air is just this really complicated mess of millions of millions of millions of millions of millions of molecules of nitrogen, oxygen, carbon dioxide, water vapor, all these things flying around at all different velocities, at all different directions. They would keep colliding with your calculators, and they would keep having these elastic and inelastic collisions. It would be a real mess to calculate. The very strange thing is your calculator, when you throw it, it doesn't actually have to calculate anything. It just does the really complicated physics. And frankly, if you remember when we did this in class, got weird and philosophical. It's bizarre that this works. The question is, why does math work so well at describing the physical universe? So there was this guy, Eugene Wigner, Nobel Prize-winning physicist and mathematician, who wrote this wonderful article called "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." And again, we're not going to do this, but you could follow this link. It's a link to the article. You can read it. Where he describes this idea. So you remember I also talked about this stuff. This is the bell curve, the Gaussian distribution, the normal curve. You see this all the time in statistics. Anytime you're measuring something and you expect there to be an average kind of result, but some random variation one way or the other, this is the kind of distribution you're going to get. So if you were doing, for example, test scores, if you were doing the SATs, there would be some average test score, right, like here, and then there would be a predictable amount of people who did a little bit better. So within one standard deviation this way. And there would be about the same amount of people who did a little bit worse. So they would fall within this one standard deviation here. And then a smaller amount of people would do a lot better. So between 1 and 2 standard deviations away, and about the same number of people would do a lot worse between 1 and 2 standard deviations the other way. And then very few people would do better than 2 standard deviations, or even fewer would do better than 3 standard deviations better. And same idea. Fewer would do worse than 2 or worse than 3. So you've got this very complicated, scary looking bit of math here that describes this Gaussian normal distribution. This is the bell curve. So it's very weird. Here's E, Euler's number. You'll learn that in math, pre-calculus, calculus, if you haven't started learning it yet. But the strange thing is, you've got this guy here too, pi. Pi shows up. Why does pi show up in this problem? So what exactly is pi? Pi is the ratio of the circumference of a circle to its diameter. So if you take any perfect circle and measure its circumference all the way around and divide it by its diameter, you get pi, 3.14159, and it goes on forever. So the very strange thing is circles and their circumferences and diameters don't really have anything to do with the random distribution of test scores. And yet, for some reason, pi shows up in this formula. It's very, very strange. Pi does this all the time in math. You'll be doing something that has nothing to do with circles, and eventually the math will lead you back to pi. It's just weird. It's bizarre. It's unreasonable. Then there's this other idea. Bernard Riemann, great mathematician in the 19th century, so the 1800s. He did this really bizarre math just for the love of math, because he was really good at math and he wanted to do this weird math that no one had ever done before. So he figured out how to do geometry and calculus in more than 3 spatial dimensions. He could do this in n dimensions, just give him a number of dimensions. He could figure out how to do all the geometry and calculus there, with the added little wrinkle going on that you're now allowed to curve the dimensions. So instead of trying to do geometry, imagine drawing circles and triangles and things on a flat piece of paper. If you were to, roll the piece of paper, if you were to try to do this all on a sphere, so your dimensions can now be curved. So again, he did this back in the 1800s for no reason at all, other than that he loved math, but he didn't see any practical application for this at all, because how could anything this bizarre have anything to do with anything? And then famously, about 50 years after Riemann died, Einstein published his very greatest idea, the law of general relativity. He published that in 1915. And in that idea, he figured out that Newton's ideas of gravity were actually a little bit wrong. They're incomplete. They don't cover everything. And you have to think of gravity as a curvature of 4-dimensional space-time. So instead of thinking of 3 dimensions of space, X, Y, and Z, you've got to also kind of deal with time as a dimension. And these dimensions can curve. And that's what gravity is. So the weird thing is that when Einstein needed to figure out the math for this idea, this math had already existed. Riemann had done the math already for no reason at all. He did this math. And then when Einstein needed this very abstract, very crazy math, it was already there. Riemann had already done it. This happens a lot. Anytime a physicist is working on something new and they need crazy math that's never been done before, turns out someone probably already did that math. Because people who love math, and they do it for the beauty of math. And it just ends up that math is unreasonably effective in the natural sciences. So the big questions are, why does the universe work this way? Why does it obey mathematical rules? Could it work any other way? What exactly is math? Is math invented or discovered? When someone's doing new math, are they making up new things, or are they discovering something about the universe or truth, or what the hell exactly are they doing? Very deep questions. There is totally there are branches of philosophy that deal with the philosophy of science and the philosophy of math. And yeah, they're very, very bizarre questions, but very deep, very profound. I like to think of these, and I don't know the answers to any of them. I do like to think that math is discovered. It's an ongoing debate in the philosophy of math. So that's it. We got up to slide 51. And I have no idea how long this video has taken, but I'm glad to be cutting it off here. So hopefully you found that interesting.